lecture is very simple. Most of the things that we do are related to AI, but we wanted to bring experts from topics that are not restricted to AI, but from more topics into our lecture series. So that's the reason why we started this Extra Mural Lectures. And today I am very proud and happy to introduce Brahma Gopalchetty. So I'll not take more than 1 minute on this slide. I'll hand over to Brahma right after this, but I want to speak a few words about Brahma. I have known him for the last maybe 1.5 years. We have worked together for one of the papers that he published recently in a very high impact journal. And Brahma is a recent graduate from UCL London. He's been the gold medalist throughout at his undergraduate as well as his masters. He is the UCL student champion 2023-2024. And more importantly, he is also now a Royal Astronomical Society fellow. This is a very, very prestigious achievement for anyone. It's very difficult to get. It's a very rare, exceptionally rare feat. So we are all lucky to have Brahma here to present his work on which is titled as From Concept to Cosmos, Envisioning a Titan Exploration Mission. So basically the talk is about how he designed the concept called Tara for Titan exploration. And I don't want to talk anything technical about it. I'll leave it all for Brahma. So I'll make you the host, Brahma, and you can start sharing your screen. I'll stop sharing here.
Yeah, sure, sir. Yeah, so I hope you're able to see my screen and all the participants as well. Is everyone able to hear me?
Sorry, Brahma, I just had to reclaim the host just to admit a few more students. But your screen sharing is working, so I can stay as the host and you can continue. We can hear you. Yeah.
Yes, sir, that would be amazing. Thank you so much. All right. Hello, everyone. My name is Brahma, and thank you so much, Sridhar sir, for such a great intro of mine. Today, I'll be delivering the lecture on From Concept to Cosmos, Envisioning a Titan Exploration Mission. I will walk all the participants through the insights and development of a futuristic deep space mission concept, how it's being conceptualized from paper and pre-phase A conceptual studies all the way to be launched on a spacecraft and to acclaim the highest science return possible. So I'll start with my research in a nutshell. So I'm a recent master's graduate specializing in space science and technology from University College London, UK. For my master's dissertation, I designed and formulated an innovative deep space mission concept called TARA, Titan Atmospheric Research Ascendant, which I'll talk a bit later in the presentation. So you all can see in the left-hand side the report as well as a beautiful picture representing the Titan's biosphere and its dynamic ecosystem, which I'll talk about in the later presentation. For my group project, I co-led the Spacecraft and Subsystems team for HERO mission concept, which stands for Heliospheric Exploration and Interstellar Research Observatory. So this was conceptualized as a NASA mission, which you can see here on the screen. Heliosphere is the boundary of our solar system, and it is generated by sun's magnetic field, which protects our solar system from variety of cosmic threats such as galactic cosmic rays, solar radiation pressure and debris and material from the interstellar medium. So understanding the heliosphere is extremely important in the sense to understand the dynamics and functioning of our solar system. And in the right top here, you can see the spacecraft which I designed, as well as I was in charge of formulating and designing the attitude and orbit control subsystem, as well as the propulsion subsystem for the spacecraft Hero, which was conceptualized to explore the heliosphere as well as the interstellar medium. Some of the outreach and networking events which I was a part of, here you can see a British Interplanetary Society conference meeting wherein I was involved in docking the ISS with a Soyuz spacecraft. This was quite a simulated environment and a fun activity, I would say. Here are some snippets of the lectures which I have taken in the past with UKRI, STFC, Science and Technology Facilities Council. This photo on the left, this is a very special picture for me. This photo was taken by ExoMars Rosalind Franklin rover. The MSSL Mullard Space Science Laboratory, the pioneering space science lab of UCL, is involved in leading the panoramic stereo cameras for this mission. So I was fortunate enough to work with the MSSL team in the development of ESA SpanCam for the ExoMars mission, as well as here you can see the Mars Yard in Airbus in the UK, wherein the rover is being tested on this artificially simulated environment, which is sought to replicate the Martian environment here. Also, this is a certificate of mine wherein I received the runner-up award for my talk on Titan exploration mission and the research I did with UCL. So now, since we have broken down the ice a bit, let's start with the presentation. So this lecture would be divided into two parts, the science part as well as the engineering part, in order to reach maximum of the spectrum. So the science part is designed to give you an insight of why Titan is important and it is a dynamic target for solar system exploration. So I'll be talking you through the significance of Titan, the open questions and the unanswered questions about Titan, some previous missions to Titan exploration, which were launched by top-level space agencies such as NASA, ESA, and ISRO. Opportunity for a future mission. What are the key elements that the previous missions were unable to answer, and why do we need a future mission towards Titan? Then I will talk about the mission development process. In order to envision a Titan exploration mission, you have to really understand how people and scientists in major space agencies like NASA and ESA formulate a space mission concept. So I will use the space mission concept which I formulated as an example to explain you the process. I'll talk about Tara's mission architecture, the risks and limitations involved in designing a deep space mission concept, and some of the preliminary conclusions to hold. So let's start with Titan and its significance. So why is Titan so much important in terms of the rationality of exploring the solar system? Titan is one of the most enigmatic bodies in the solar system and a prime target for future space exploration missions due to its dynamic ecosystem. The complex interplay the Titan has between geology, hydrology, meteorology, and aeronomy makes Titan a very unique body in terms of astrobiological significance. And there have been multiple elements found in Titan which can harbor microbial life. And understanding Titan will certainly aid us to understand the origin and evolution of life on Earth as well. Titan's atmosphere is a unique atmosphere, and I have to say the only nitrogen-rich atmosphere apart from Earth in the solar system, which is distinct and well stratified, right? So the atmosphere of Titan is very similar to the atmosphere Earth had in its primordial days, which means in early stages of Earth's formation and evolution, except for the lack of water vapor, which Titan's atmosphere doesn't have, the atmosphere of Earth and Titan were very, very similar at a certain point in the timeline. So understanding Titan's atmosphere and its interaction with the other elements of the biosphere will help us understand how Titan's atmosphere is very unique, as well as the astrobiological significance it holds. Titan houses an active meteorological cycle with methane as a working fluid. You all will be surprised to know that it literally rains liquid methane on Titan. So understanding the climatic conditions, weather conditions, and the meteorological cycle of methane on Titan will definitely aid in our understanding of the hydrological cycle, which we have on Earth, obviously with water. But both of the planetary bodies, Earth and Titan, are very, very similar in this aspect, and it will certainly aid our understanding in Earth's climatic and weather conditions as well. Titan hosts seasonal weather patterns, wind and rain patterns, very, very similar to Earth, and it is the only body in the solar system to do so. Titan also hosts a lot of geological features which are very, very similar to Earth. So Titan has dunes, lakes, rivers, and seas. But in contrast, in resemblance of, we have lakes and seas of liquid water on Earth, whereas we have lakes and seas of liquid methane and ethane on Titan, because it literally rains liquid methane and ethane from the atmosphere and stratospheric clouds. Titan also has canyons, deltas, network of channels, impact craters, mountains, as well as cryovolcanoes, which makes Titan's geology almost very, very similar to that of Earth. If we have to understand the Titan's internal structure, so you can see in the picture here, so Titan's internal structure has three important layers. So crust, which is made up of ice hedge, which is hexagonal crystals. So the Titan's crust is completely made of ice. There is a subsurface ocean beneath the ice of ammonia-rich liquid water, which is very, very important for us because that's how ammonia-rich liquid water is delivered to Titan's surface via cryovolcanism, which I'll talk about later in the stages. And then the Titan has silicate core, and which is wrapped, by various layers of ice. And this is a firm ice called ice 6, which is a lot firmer as well as a lot more dense. Here in this picture, you can see the beautiful interplay within Titan's biosphere and how Titan's different layers interact with each other, as well as how Titan emerges to be one of the prime target for future space exploration. Talking particularly about the atmosphere and prebiotic environment, Titan's atmosphere, as I said, is the only nitrogen-rich atmosphere apart from Earth, and it generally acts as a huge chemistry lab, in my opinion, because Titan's atmosphere is an organic reservoir which synthesizes potential biomolecules which are precursors to astrobiological significance. Titan's atmosphere obviously is way more denser than Earth. The column density of Titan's atmosphere is 10 times of that of Earth, as well as Titan's atmosphere is completely opaque, making it challenging for the previous space mission to directly monitor and capture high-resolution images of the surface. And the reason why it's denser is due to gravitational compression, right? Composition of Titan's atmosphere is 94.2% nitrogen, a very small percentile of methane and ethane, around 5.65%, some trace percentile 0.1 to 0.2% of hydrogen, and all the rest of the elements fall within the troposphere. So the entire atmospheric and prebiotic synthesis has been presented here. As you can see, this is a graph with altitude on y-axis and temperature on the x-axis. So this is basically the temperature profile through the atmospheric layers of Titan. And you can also see the pressure distribution. So what happens in Titan's atmosphere is pretty interesting in terms of why we want to study specifically its atmosphere is the photochemically generated organic species are of prebiotic interest. So what happens is due to the photolysis of methane by the UV rays of the sun, the methane breaks down into long carbon chain anions, right? And then those carbon chain anions basically descend from Titan's upper atmosphere all the way to the lower atmosphere, and they coagulate and coalesce. They mix with other constituents in their vicinity, and they produce a number of very important hydrocarbons and nitriles, such as propene, polycyclic aromatic hydrocarbons, benzene, even amino acids and nucleotides, which are found in our DNAs. And that's the reason why everyone in the scientific community believes that enough organic material is present in Titan in order to start a chemical evolution, because life can easily sustain on Titan, and there are various arguments which can be made in support of this. So, and also I'm very happy to let you all know that my MSc supervisor, Professor Andrew Coates, was actually the first person in the world to actually discover the abundance of heavy negative ions in Titan's upper atmosphere. So he is considered to be the pioneering scientist behind Cassini-Huygens, as well as he used the Cassini-Huygens data to study Titan's atmosphere. Talking about the troposphere rains, so it rains liquid methane, ethane, and other organic compounds right onto the Titan's surface from the atmosphere. So Titan's atmosphere, a vertical section of it can be seen in the right-hand side here. So the atmospheric layers are very, very similar to that of Earth. Again, as I previously mentioned, Titan's atmosphere is already very distinct and well stratified, which means by density, temperature, as well as composition, the atmospheric layers are very, very well organized in Titan. So a similar fashion is seen here. We start with troposphere, which is nearest to the surface level of Titan, followed by stratosphere, mesosphere, as well as thermosphere. But something to keep in mind is Titan's atmospheric density to surface gravity ratio is very high, which means the surface gravity of Titan is extremely low in comparison to the atmospheric density, which makes Titan's atmosphere an extended atmosphere. It actually goes up to 1,200 kilometers, whereas on Earth, the Earth's atmosphere doesn't go as high. So Titan's atmosphere is dense as well as extended. So Titan's atmosphere is an organic reservoir of hydrocarbon, nitrogen, nucleotides, as well as amino acids. And the atmosphere plays a crucial role in delivering all these constituents to the surface, which makes Titan very important to study the pre-biotic evolution, which we call the evolution of life on other extraterrestrial bodies in the solar system. Every interplanetary deep space mission is a function of science goals as well as mission objectives. And how do we understand that these are the science goals which we need to address in our upcoming deep space mission concept? Is by analyzing and building on the wealth of data procured by various previous multiple missions to Titan, such as Pioneer 11, Voyager 1, Voyager 2, and Cassini-Huygens. And we basically build on our understanding of Titan and identify potential open answers, which are open questions, which are partially answered or unanswered about Titan. And then we basically target some of these key questions for our space missions to be developed and formulated for. So the open questions can be easily divided into three regimes, as I have done here. However, the regimes can be far more extended and far more diverse as well. But in my opinion, it can be divided into three sections. The first science goal is Titan's atmosphere. The second science goal is Titan's geology, as well as the third section science goal is Titan's habitability. So what are the open questions in Titan's atmosphere? So if we talk about open upper atmosphere, so we are not completely sure about the role of ion neutral chemistry in upper atmosphere. As you can see in this picture here, the UV photolysis of methane happens and massive positive ions and electrons are generated in Titan. And then it grows via coagulation and coalescence to form polycyclic aromatic hydrocarbons. And then aerosols are deposited in between 150 and 400 kilometers within Titan's atmosphere. And these aerosols are very, very important for us because these aerosols contain a variety of hydrocarbons and nitriles, which are important for emergence of life on Titan. So oxygen incorporation is very important here. We are not completely sure about the origin and dynamics of upper atmosphere as well as the physical processes of ionosphere and thermosphere. If I talk about middle atmosphere, this is the region where the circulation and overall dynamics of Titan's atmosphere is housed. So Titan's atmosphere is a super rotating atmosphere, which means the atmosphere of Titan rotates faster than the Titan's rotation itself. So we need to fully comprehend and understand the reason why Titan's atmosphere is super rotating, why the polar vortices form and evolve on Titan, and we have to consider the structure and composition of stratospheric clouds, because all these aerosols coagulate and they form big clouds, and those constituent which are housed within those clouds rain down on Titan's surface. So it's very important to understand the structure and composition as well. And finally, properties and of aerosols and in Tholin haze. So if I go back to this slide, you can see between troposphere and the stratopause, the ending of stratosphere, there is a layer called main Tholin haze layer. So this layer is an outcome of the photochemically generated species from the top of Titan's atmosphere, and they settle down in this region of Titan's atmosphere. And this is very, very important because analysis of the aerosols and dust particles which are present in Tholin haze layer is tells us a lot about the vertical and horizontal profile of Titan's atmosphere, as well as the entire composition and constituents, starting from the upper atmosphere down till the troposphere. Lower atmosphere houses the entire climate conditions, weather conditions on Titan. So we have to understand more about the methane cycle of Titan. We have to understand surface winds, storms, cloud formation in Titan's troposphere, as well as the near surface processes. As I have already said, it literally rains down liquid methane on Titan's surface. So obviously Titan's surface has many markers of erosion, rain deposits, and we have to understand the composition of lakes and seas as well. So that becomes important in the vicinity of the lower atmospheric study. The second science goal, Titan's geology. So as I have already mentioned, Titan has dunes, lakes, seas, all the geological elements which you can think of similar to Earth. So some of the key geological features comprises of aeolian plains and dunes, fluvial processes, and seas impact craters and cryovolcanoes. So about the aeolian plains and dunes, we are very interested to understand the geographic distribution, formation, and evolution of these dunes, and how the atmosphere affects the evolution of these dunes. Morphometry of equatorial regions and composition of sand is extremely important. So in contrary to the Earth, where you have the silicate based sand, Titan's sand actually is very different because Titan has an icy bedrock, which you can see in this picture here. So the Titan's crust is completely made out of ice hedge. So the Titan's sand is like a sand of ice crystals, which is washed down by methane via flash floods when it literally rains on Titan. So composition of sand, granulates, and particles is also extremely important. Fluvial processes and features. So we have Titan also, since Titan has lakes and seas, there is no surprise that each lake, each sea, and each methane and ethane ocean on Titan has a network of rivers. So geographic distribution and how exactly these river networks form is extremely important. And the composition of eroded material is important also. And canyons, lakes, and its connections with channels is very important to understand Titan's geology. If I talk about seas and impact craters, so composition and evolution of lakes and seas comes into picture. History and evolution of cryovolcanism on Titan's surface is important because cryovolcanism on Titan is a phenomena which connects the subsurface layer of Titan to the surface. Because as I have said, beneath the ice crust, Titan has an ocean of ammonia-rich liquid water. It has been proven using the hyperspectral measurements as well as the radar measurements via Cassini-Huygens. So we are very curious to understand if this subsurface water is delivered to Titan's surface via cryovolcanism. So this becomes very important. Biosignatures and properties of subsurface ocean, as we said. So the subsurface ocean is expected to be beneath 50 to 100 kilometers of Titan's icy crust. So if we have powerful machinery, if we can dig deep into Titan's crust and reveal the subsurface ocean, we can definitely investigate if there are any biosignatures, if there is any microbial growth. Because even though Titan's temperature overall is 94 Kelvin, which is very, very cold, because the amount of solar radiation flux which comes to Titan is negligible in comparison to Earth. Since the subsurface liquid water is mixed with ammonia, it's ammonia-rich liquid water. Ammonia actually keeps the liquid water beneath Titan's crust in a liquid form. It doesn't freeze. So it's called eutectic mixture. So if you are into chemistry, you might know this. But ammonia, when mixed with water, can sustain water in a liquid form, and ammonia retains water in its liquid state at negative 97 degrees centigrade beneath Titan's surface. So it is very, very important to understand this subsurface ocean and its properties. And lastly, the correlation between atmosphere and geological features. As I said, Titan is a complete dynamic ecosystem. So understanding the interactions between atmosphere as well as geology can also teach us a lot about the history and formation of Earth, because Titan in its current state is very, very similar to that of primordial Earth. So this can not only address if there can be any forms of extraterrestrial intelligence or extraterrestrial life on other planets, but it can also answer unanswered questions which we have about the formation and evolution of Earth. Finally, we have Titan's habitability as one of the most important science goals. Titan checks all the boxes for potential habitability, including the presence of a stable substrate. Titan has energy sources. Titan has complex organic reservoir of elements, as well as Titan has a stable environment. So Titan checks all the boxes for habitability. So we want to understand the nature and quantity of material exchange between subsurface and subsurface via cryovolcanism, which I talked about earlier, to understand if there are any habitable places on Earth, on Titan, if we can find out. We want to understand the organic material synthesis and the physical and chemical processes associated with it, as well as signs of microbial growth, if any, on the surface of open lakes and seas. Because Titan has very significant benefits, since the working fluid on Titan is methane, not water like Earth. Methane is actually very stable, because we all know that water is an excellent solvent, right? Methane, on the other hand, can sustain microbial growth without dissolving them on the surface. So there could be microbial life found on the lakes and seas of methane on Titan. Whereas on Earth, it's not that possible, because if anything wants to grow on the surface of the liquid water on Earth, since water is a very powerful solvent, it will dissociate and dissolve the organic growth which happens. We are also interested to understand the chemical reactions and evolutionary traces of pre-biotic environment on Titan, and the chirality of biomolecules in Titan's atmosphere and surface. So as you can see here, Titan's global structure has been represented in this picture. So you have an organic rich atmosphere as well as surface. You have decoupled outer shell. You have global subsurface ocean beneath the ice crust. And then you have high pressure ice shell, which I talked about. And Titan's atmospheric density to surface gravity ratio makes it extremely easy to fly on Titan. It is also hypothesized that, if you land on Titan and you strap a wings to yourself and you can run and have a jump start, you can actually fly on Titan, because atmospheric density is so high and the surface gravity of Titan is so low, which can be depicted here on this picture. And Titan is gravitationally and tidally locked with Saturn, its parent planet. So only one side of Titan is always visible to Saturn, right? So one Titan day is equivalent to around 15.945, approximately 16 Earth days. And obviously the revolution period is also the same since it's gravitationally locked. Now let's talk about some of the past missions to Titan exploration. I wanted to touch this so that you can easily appreciate the amount of effort it takes to explore these dynamic celestial bodies. So Pioneer 11 was the first spacecraft to fly through Titan. And Pioneer 11 concluded in 1979 that Titan is too cold to support any life, and which is true to some extent because the temperature of Titan is the only counter argument regarding the habitability of Titan. Apart from that, there are all the arguments and all the discoveries about Titan which we had are in the favor of Titan's habitability. Voyager 1 and Voyager 2 again are flyby missions which pass through Titan before leaving the heliosphere or before leaving the solar system. Voyager 1 and Voyager 2 were the first spacecrafts to remotely uh, study Titan as well as remotely make out the density, temperature, and structure and mass of Titan in general. Cassini-Huygens is the most important mission till date for Titan exploration because it paved a golden era of Titan exploration. Huygens lander became the first man-made object to ever land completely on Titan's surface. And since the demand for in situ exploration of Titan is exponentially increasing year after year, we are in the need of demonstrating some aerial vehicles which can descend into Titan's atmosphere and make in situ measurements rather than remote measurements from a distance, wherein you don't have that clarity and you don't have direct measurements, I would say. So I have a video here. So I'll just play this. Hmm. Titled Musical Descent to Titan. So this video actually shows the Huygens landers landing on Titan. Yeah, before the video, Sridhar sir, can you confirm if the video is audible to you and to the participants? I hope the video is audible to you all. I'll play it once again.
The sound is not coming. Maybe in the sharing, when you share the screen, you have to click a button saying share screen sound.
Just a minute, sir. I'll check if that is the case.
Yeah. So you'll have to stop sharing once and maybe reshare.
Sure, sir. Definitely. I'll do that.
Sharing, I think there is an option to tick.
Yeah, sure, sir. I'll do that.
Yeah.
Sure. Sir, are you able to see my screen now?
Yeah.
I think now the audience can hear the sound.
Yeah.
So what this is basically it is basically resolving each and every component during descent. So this is the Huygens lander descending near Titan. I'll just skip some bits. So the reason why it's called musical descent is it makes a good noise. I'll just skip a little bit. Yeah. Till 3. Okay. Yeah. Yeah, so once it has landed, yeah, there you go. Yeah. All right, I'll stop the video here. So as you can see, Huygens lander became the first unmanned robotic technology to land on Titan. And there is a demand for more in situ elements which can descend through Titan's atmosphere and make measurements to understand Titan's biosphere in general. Some of the mission concepts to Titan exploration. So, apart from the previous missions which I have already described, there have been many mission concepts as well before this to understand Titan in general. So, some of the missions are enlisted here. So, here you can see Titan Saturn system mission, which comprises a pressurized balloon, a lake lander, as well as an orbiter to study Titan. There is Titan Airship Explorer, as represented here, which is a pressurized air balloon airship to study Titan. This is Titan Mare Explorer, which aims to descend onto Titan's lakes and study the structure and composition of Titan's lakes and seas. This is Aviator, uncrewed drone, high-speed airplane, which traverses through Titan's atmosphere. And this is a futuristic NASA mission which has already been approved, which is called the Dragonfly mission, which is about to go to Titan and reach there by 2028. So this is a UAV, unmanned aerial vehicle. It's actually a rotocraft. It's a UAV with like 4 blades to fly on Titan's atmosphere, and it will sample Titan's atmosphere as well as the near surface environments. So the opportunity for a future mission to Titan is immense because the NASA's New Frontiers program, as well as the ESA Voyage 2050 announcement of opportunity, both these programs are encouraging scientists and researchers to propose new missions to Titan. So there can be a plethora of future mission configurations such as flyby, rover, orbiter, sample return missions, lander missions, maybe a hybrid of these two. There can be any atmospheric probes or some technology demonstrators which the crowd hasn't seen before. So the opportunity for a future mission to Titan is immense, and all the space engineers and scientists across the world are developing futuristic missions to explore Titan. Now, finally, let's come to the engineering part of it. We are running behind time by a little bit, so I'll quickly try to traverse you through this. So a simplistic approach would be to follow the NASA project lifecycle. So this is actually broken down in multiple phases, as you can see in this picture. So it goes from pre-phase A to phase E, and you have steps. You start to conceive, you formulate the mission, design, build, you have testing, launch, and you have the operational phase, and then utilization and disposal phase. And if you are a little bit nerdy like me, this is the actual plan, which goes along the desks of NASA and ESA. And this is the project lifecycle phases from pre-phase A till phase F. This is how a mission development is put forth in the practical setting. So it starts from concept studies, and it then once it is approved for formulation, it goes to pre-phase A, which is concept and technology development. Then it goes to preliminary design, and then it goes to final design and fabrication. Then the manufacturing, assembly, integration, and testing of space instruments as well as the spacecraft body takes place. And once all the checklists are correct, then it goes to the operation phase. It is launched via launcher, and then decommissioning and disposal takes place in phase F, which is the closeout phase. So this is actually a very good concept map, I would say, of the NASA mission development cycle. This is how NASA, ESA, and other space agencies formulate their missions. So the Tara mission, which I have devised, is in the pre-phase A concept study phase for now. I am expecting this mission concept to go through all the phases in near future, as well as I'm proactively working towards getting this mission incorporated with the space agencies. Let's talk about the Tara mission concept, which I formulated during my time in UCL. So some of the key points I want to touch upon. So I formulated this mission to be a dual element architecture mission comprising of a Titan orbiter as well as Titan's ornithopter. Because since being from an aerospace background and utilizing the key aspects of Titan's atmosphere, aerial vehicles traversing through Titan's atmosphere makes a lot of sense because of the Titan's high atmospheric density to surface gravity ratio. Aerial vehicles can easily fly on Titan's atmosphere, and if this aerial vehicle can be flown like an ornithopter, a bio-inspired aerial vehicle, which is a UAV in the form of a bird, then obviously we can utilize the tailwind conditions of the atmosphere of Titan to push the ornithopter, utilizing as low propellant and as low fuel as possible, and giving us a global coverage of in situ exploration of Titan's atmosphere. So the orbiter is aimed to map Titan's atmosphere and near surface environment via comprehensive mapping. And ornithopter is an in situ aerial vehicle which will descend into Titan's atmosphere and make measurements as it descends. So some of the advantages and limitations here. So there are a lot of advantages using an ornithopter. So we have bio-inspired efficiency. We have enhanced maneuverability using the wings. It can easily maneuver through the thick and dense atmosphere of Titan, as well as it can be used for low speed operations if it wants to stall and take some measurements and observations at a certain astrobiologically significant place in the Titan's atmosphere. It can do that. And obviously it can adapt to harsh conditions of Titan's atmosphere. The biggest challenge for any aerial vehicle to survive in Titan's atmosphere is its temperature, because as you saw in my previous slides, the temperature of Titan's atmosphere is very low. So heating of this aerial vehicles is always a challenge which space engineers have to keep in mind to design any in situ exploration vehicle. Some of the limitations, as I talked about complexity in design and engineering, we have very limited payload capacity. So every space mission which existed till date is always an outcome of trade-offs, right? So you can't have both the things operating for you at the same time. You always have to compromise on one or the other. So if you are completely bundling yourself with high payload on one aerial vehicle, you're maximizing your chances of potential failure, single point failures, and the entire mission going down the drain. And if you are basically, if you are thinking to launch, let's say, a swarm of ornithopters or a swarm of UAVs, which will monitor Titan's atmosphere at a time, then you have like certain problems, like you have to establish communication between all those individual drones which you have released. And so really scientists and engineers work together to figure out these trade-offs, limitations, merits, demerits, everything, and then come up with a mission concept. So this is the mission overview. So some of the key mission goals are represented here. So Tara mission aims to study origin and evolution of atmosphere and governing parameters. And yeah, by the way, I forgot to mention, you have seen the previous slides of science goals, right? So I'm actually targeting science goal A as well as science goal C, which is Titan's atmosphere and Titan's habitability. Because you also have to understand that you can't address all open questions at a go using only one space mission. So each and every space mission has its own set of limitations, and based on that, we have to target the open questions which have highest potential, and so that the mission can be cost effective and highest science return could be possible. Because each and every mission has to successfully work, and once you launch it in that environment, you can't do anything, and it should entirely run on autonomy, right? So once you have launched a space mission, there is no turning back, and you have to ensure that with minimal cost, the output of science should be highest. So this is the model payload. So I have provided a science payload table for Tara mission, which I have selected. You don't have to go into details of all this. Basically, it's just a combination of spectrometers, high resolution imagers, magnetometers, and radio occultation experiments to understand density, temperature, and composition of Titan's surface, as well as high resolution cameras are present to basically map Titan's near surface environments, take some pictures, as well as analyze the near surface environments. The suite of Titan's orbiter science payloads and Titan ornithopter science payloads is obviously different. because you have to tailor that in certain way, because orbiter here is a bigger vehicle. So there can be a lot of instruments accommodated, but ornithopter is very, very specific. So you need to be, this is again called subsystem packaging, wherein if you are designing a vehicle, you should strategically place each space instrument in a certain way so that everything works together in conjunction. With every mission comes mission trajectory and timeline. So I won't go through much details with this because it's like extremely technical. So, but you can see the overall mission profile as represented here. So I have proposed the Tara mission to be launched on Ariane 62 launcher by 1st January 2030. And this is actually a very impressive tool. It's called the NASA Trajectory Web Browser, which gives you the exact trajectory, the most optimal trajectory based on your inputs. And here on the right, the Tara mission Delta V budget is represented. So basically, Delta V budget is something which would be known to the astrodynamics engineers. Delta V is basically the change in velocity imparted to the spacecraft or satellite via multiple phases of its mission. So all the space missions are designed to lower as much delta V as possible, because in order to have some delta V, you have to fire some thrusters, right? You have to fire a bit of your fuel, and you have to run that in order to get the velocity separation from that, right? So this is the step-by-step delta V budget, starting from the low Earth orbit insertion, then Earth departure, Jupiter flyby, and then ornithopter targeting, and then Titan orbit insertion, and then aerobraking, and then circularization around Titan's orbit. Coming to mission operations and lifetime, so I have enlisted the most important mission elements here. So Titan orbiter as well as Titan ornithopter both would be 3-axis stabilized, which means they will have some momentum imparting thrusters on them in order to direct them in 3D Cartesian coordinate system, right? So in space, we call it 6 DOF, 6 degrees of freedom. So we have 3 axes of translation as well as 3 axes of rotation. So both orbiter and ornithopter has to be stabilized and should be protected from the external forces, right? And for power, we are using RTGs. RTGs stand for radioisotope thermoelectric generators, which are basically batteries which run on radioactive elements, right? And we have high gain antenna for communication between orbiter and ornithopter, as well as downlink communication from orbiter to Earth as well. We have to design a radiation design point as well, because Titan's highly eccentric polar orbits falls under Saturn's magnetosphere, and Saturn's magnetosphere is very, very harsh. So it has a lot of energetic neutral atoms. It has a lot of highly energetic protons and electrons. So we don't want any electrical and magnetic instabilities within our spacecraft as well as our ornithopter. And for science traceability matrix, mass and power budget, I would suggest the audience to scan this QR code. I haven't put this because it is very technical. So when after the presentation, if anyone wants to ask about this, I'll be happy to answer those questions as well. Finally, we talk about risks and limitations of Tara mission. So we have a spectrum of risks and limitations here. We have engineering and technical challenges, scientific limitations, operational risk, logistical and budgetary constraints, regulatory, environmental, and ethical concern, as well as technology and knowledge gaps. So you can see, and I have actually put a suggested reading reference here. So this is actually a very important document, Future Missions to Titan, Scientific and Engineering Challenges by Caltech. If you are interested, please find this document online. It is completely free to read, and it very beautifully represents the threats and challenges for a future Titan mission, which could be encountered. So finally, we end it off with preliminary conclusions. So some of the preliminary results of Tara mission concept. So the feasibility has been established. The technical and logical feasibility established for exploring Titan's atmosphere. And this mission offers high scientific potential because this mission builds up on the data and wealth accumulated by the previous space missions, particularly Cassini-Huygens. So the unanswered questions which were left after Cassini-Huygens were tried to address in this mission, as well as technology demonstration. So bio-inspired vehicles, ornithopter is obviously a novel concept. No space agency has done this before, but there has been some controversies regarding utilization of drone for planetary exploration, because the only drone, the only aerial vehicle to flow on a different atmosphere and planet till date is the NASA's Ingenuity helicopter, which landed on Mars and took flight. So the feasibility and technology demonstration of aerial vehicles for planetary exploration is starting to progress, but in no way it is completely reliable. So obviously, future aerospace engineers and scientists are working in conjunction to effectively incorporate aerial vehicles for planetary explorations. And Tara mission is also a step towards it, right? So currently, the Tara mission is in pre-phase A concept studies. I have already submitted it as a proposal to the leading space agencies, as well as a research article based on this mission is in pipeline right now. So once it is out, I'll highly encourage you all to go check it out, because the entire mission development process, starting from studying the current science and literature about Titan till the hooks and crooks of of the spacecraft engineering, as well as the development, is all mentioned in the research article. So I'll highly recommend that. All right, these are some of the references and bibliography which I used. So audience can scan this QR code and go through all of this material if everyone wants. All right, that's the end of my talk. Thank you so much for your patience, and I really appreciate you all, because you took off some time on a weekend to listen to the talk. And now I'll open the panel for possible discussions. Thank you so much.
Thank you so much, Brahma. This was an amazing talk. Folks, if you have any questions, feel free to ask in the chat itself. And we'll have 5 more minutes for for chat. And if you don't have any questions, we can wind up. But otherwise, Brahma will be available for another 5 minutes. Brahma, can you share your email in the chat so that people can reach out?
Yeah, definitely.
Okay. So that way, if someone thinks of a question later, they can just email you.
Yeah, sure.
Yeah.
So I'm sharing my email, and yeah, I have shared it. So now, prospective students can get in touch with me if they have even more questions. I'll be very, very open to consider questions. Sir, shall I open the chat and look for questions? All right, if anyone wants to ask me a question, they can unmute now and ask me directly, because I'm not able to go through the chat for some reason. If there is an option to maybe raise your hand, that would be great.
Hello.
Yes, Dev, go ahead.
Yes, sir. My question is that how you became so focused early in your life, during your BTech in aerospace engineering. I want to know
Okay.
your mindset. Like,
Okay, that for unfortunately, this question is not at all relevant to the talk which I presented. But yeah, it's I mean, it trickles down to having a very clear-cut passion and liking for what you do. So I can't brief much on to how I'm passionate about space science and engineering. But I would certainly say that you all should, try to build a priority list, and then, you have to uh, make sure that each and every step you take in your academic career leads you to that common goal and objectives. You have to put a timeline. People don't have unlimited years. People have limited years on Earth. So yeah, definitely this is an important factor because uh, I mean, your passion is only a passion if it doesn't have a timeline to it, right? If you combine passion with timeline, it becomes your ambition. So once you have a clear-cut ambition, and if you have a timeline, and if you have clear-cut objectives of what you want to, do in life, and then again the further steps will come. There will be path about how you will go ahead and take up this journey, and then you have to plan your journey as well. Yeah. So I understand the enthusiasm, resources, as well as awareness of space science and engineering in India specifically is very, very minimal. So I would suggest everyone to, get out of your comfort zone and try to explore as much as possible, because I'm not completely sure the entire audience poll here. I mean, the background of audience who are listening to me. But if you are a student, then definitely it's the right time to do so. Yeah. Okay, any more questions? You can raise your hand and then I will, I think, unmute, because as the host, I can see the option to unmute, but I'm not completely sure. Okay, Srinivas.
Hello, sir.
Yes, Srinivas.
Sir, am I audible?
Yes, you are.
Sir, I have this doubt, like there is any information about this radiation interaction in this atmosphere of Titan we are speaking of, and the other secondary radiation caused by nuclear fragmentation. And you also mentioned that it was tidally locked to Saturn. There'll be impact of charged particles coming from Saturn. So, in order to know this
Yeah.
atmospheric
So,
very well,
y- yeah, definitely. So, every atmosphere has something called radiation budget, right? Uh, every atmosphere is different because the density, temperature profiles, wind profiles, composition is different, right? So every planet, every atmosphere has a certain radiation budget which the spacecraft has to endure if it wants to survive. When I was presenting, if you have seen that, the radiation design limit for my proposed mission was 15 kilorads, right? So our rads is actually a terminology for the radiation dose. So if the radiation exceeds 15 kilorads, and if your spacecraft which you're designing is not tolerant to 15 kilorads, it might break down. So this trickles down to material science, because scientists and engineers use very high radiation hardened materials if they are sending any spacecraft to high energy radiation environments. Because I mean, even for space missions to study sun, right, like the Parker Solar Probe, and if I talk about India, we have Aditya L1. So all these space missions have radiation hardened space instruments, space wire interfaces, right? To so that once they go to the vicinity of spacecraft, it is very calculated, right? It also depends on the trajectory of the spacecraft also. So it depends how much radiation dose will the spacecraft bear in a certain distance from a key object, planet or star, right? So a lot of things goes into radiation designing a spacecraft. So yeah, if you have more questions, then I can definitely share it with you. I have already dropped my email ID, so you can just come in touch with me. And there is a lot of literature already present. If you are very interested in Titan like I do, then definitely please feel free to check it out. I mean, there are you can check out Web of Science, you can check out Science Direct, you can check out uh, Google Scholar. All these literature databases wherein you can find open access papers for that. All right. Oh, you want the email ID again? Okay, just a minute. Yeah, I've shared the email ID again. The problem is I'm not that habituated to. Just a minute. I'm sorry, guys. I'm not that aware of Zoom. Yeah, I've shared it in chat. I think now you all will be. Yeah, now I think you can access my email ID. Yeah, anyone has any other questions? Else we can end the meeting. I hope you all found it interesting. Anirudh, I can see you have raised your hand. Okay, I'll unmute you.
Good evening, sir.
Yeah, good evening, Anirudh.
Sir, I would like to know your journey of enrolling at master's program at UCL and what were the challenges you faced and how did you overcome them?
Okay, again, I guess most of the audience here is very interested in learning more about me rather than my presentation, which is fine. I mean, I don't mind it at all. Yeah, navigating international journey as an Indian student, yes, it is extremely challenging. I mean, after I did my undergraduate studies from LPU, and after that, I started applying for foreign universities. So during my time in LPU, also I have developed a very good academic and research profile. That really helped me a lot in order to get into the best university I can. Because foreign universities, the graduate admissions committee has a very holistic application review process. So it's not confined to only your grades, transcripts. It's a accumulation of all the elements. So yeah, it was challenging, and I studied at University College London, which is a world top 10 university, and I was fortunate enough to work on these deep space missions. I got an opportunity, and I was also there on a 60% scholarship, I think, UCL Global Master Scholarship. So yeah, navigating everything is extremely difficult. I mean, if you guys want, we will maybe host another Vizuara lecture on navigating the graduate admissions process, and I can share my experience specifically for students like you to navigate through the graduate admissions process and enroll yourself as a master's student or PhD student abroad. All right. Yeah, I guess those who don't have any questions can leave. Thank you so much for attending. And those who have questions can remain. I'll be there for a couple of minutes. And please raise your hand if you have any questions, so that I can unmute you. Okay. Saroj, can you hear me?
Yeah, yeah. Hi, I can hear you. Hi, Gopalchetty. Yeah, thank you
Yeah,
for the
sure.
session. It was wonderful. Actually, I am also from aerospace background, but currently working in AI/ML domain, which is like artificial
Okay.
intelligence. So
Mhm.
I'm just curious, like, if there is anything that we can implement in aerospace, for aerospace especially, aerospace that artificial intelligence technology. So are you aware of that?
The answer is yes and no. One domain which I can think of wherein AI and ML specifically can be very important is in spacecraft autonomy, right? Now what happens is generally spacecraft, I mean some spacecrafts have full autonomous capability and some spacecrafts have partial autonomous capability. Like there are like many ground stations here on Earth which are used to communicate and send commands. It's called telecommunications. So scientists and engineers from Earth always keep in touch with the spacecraft and relay important information, right? So for example, let's say I'm a attitude and orbit control engineer working for NASA or ESA, and if I'm involved into a space mission which is going, like, let's say heliospheric mission, which is going beyond the solar system. So right now the process is I manually have to enter and inform the spacecraft to make trajectory correction maneuvers. We call it TCMs, right? So if the spacecraft's onboard computer can be programmed in such a way that it can automatically compute the deviation and automatically thrust itself to get into the correct trajectory, I definitely believe this can open a huge potential for AI and ML, because if the satellite can become artificially intelligent, it will definitely reduce the pressure on humans to manually override commands. So this is a topic wherein I think there is the role of AI and ML in space systems and space technology would be helpful.
Okay. Yeah.
Yeah.
I think so. Yeah. Thank you.
Yeah. Did you have any other questions?
No, right now. Thank you.
Yeah. All right. Thank you so much. Thank you. Okay, Samanyu.
Hi Brahma, can you hear me?
Yeah. Yeah, I can. Please go ahead.
Yeah, hi. I had a question about how you managed to I'm assuming that you've like sent this proposal to ESA as well, and
Yeah.
there have been some sort
Yes.
of connection between ESA and your project.
Yep.
I was wondering, as an international student, isn't that like usually a bit difficult to get inside of like anything to do with
Yeah.
ESA?
I know, but if you have right people and right network, it's possible. Honestly, I wouldn't say that the path was easy for me, because fortunately, the person who I worked with, my master's supervisor, Professor Andrew Coates, he's regarded as one of the top planetary scientists in the whole world, right? My supervisor, Professor Coates, has a decade of experience working on more than 150 plus space missions of NASA and ESA. So he has been PI, principal investigator, co-investigator for various space instrumentations. Right. I mean, currently, at the beginning of the lecture, I told you, right? So UCL is actually developing the PanCam, panoramic stereo camera, for the ExoMars mission, and my
Right.
supervisor is actually the PI for that. So he is actually
Okay.
leading the team. Yeah, exactly. So
Okay,
now
okay.
actually, yeah, in contrary to what's happening in India, you have to understand that in foreign universities and foreign countries, the gap between academia and industry is not that high. And nowadays, to effectively manage the cost bore by a space agency to launch expensive space missions, because they are in billions of dollars. So what the space missions are doing nowadays is they are actually leasing out contracts to academic institutions, and that is actually benefiting them both ways, because ESA has led an academic contract to UCL to manufacture the panoramic stereo camera. This way, ESA is actually saving a lot of money, right? It doesn't have to develop the PanCam. And the
Right.
masters and PhD students like me in UCL are able to work on the PanCam instrument. And we are also getting hands-on experience. So this is actually a win-win situation for both of us. So this is
Right.
actually how the foreign university ecosystem works. I really hope that India also takes stride in this aspect, because nowadays I actually, before leaving India, I worked with DRDO as well, and I have actually seen that this culture is not that predominant in India. I mean, unless and until you have good recommendations and you have someone known in the space industry, it's very difficult to get your hands dirty on these projects.
Right. I was
Yep.
asking because I've been so I study in Delft in the Netherlands, and I was trying to like I was trying to get my hands on some of the ESA projects that were
Yep.
going on at the university or at research institutes around the
Mm-hmm.
Netherlands. And in a
Mm-hmm.
lot of them, it was a very good fit and everything worked out until it came to the point that I was an international student and they couldn't
Okay.
grant a lot of the clearances. to
Yes,
which
that's
they
true.
had to end up saying no. And I've even like
Yeah, that's
directly
true.
contacted ESA for it and asked if there
Hmm.
were, private agencies that would,
Yeah,
I don't
yeah,
know,
I
something that
understand.
can give me an in into the space industry. And
Yep.
yeah, that wasn't so beneficial. So
Yeah, that's true. I
that's why
mean,
I asked the question.
this is a challenge for me as well. No denying the fact that the space ecosystem is closed actually. It's not that open.
Yeah,
I
definitely. I
I
mean, it's
I I definitely
understandable.
agree with that. Yeah,
Yeah,
but see, even I played a very, very minuscule part. I mean, I'm not saying that I was the principal investigator, right? My supervisor
right,
was.
right.
Yeah,
Yeah.
but it happens to be it was like luck by chance. It happened that, I mean, my supervisor was leading the team and I got to work under his guidance. That I was at least I was successful in getting a taste of how at least the space instrumentation was developed. Otherwise,
Mm-hmm.
I completely agree with you. Even I wouldn't have got the opportunity. No denying the fact. It's extremely difficult. Hopefully, let's see. Hopefully, this trend changes in near future. Even I have my fingers crossed, and I mean, I'm definitely in the favor of international students having this exposure, because I mean it's extremely important for one's overall career development. So yeah.
Yeah, definitely, because NASA has a lot of internships to offer to international students, whereas none
Exactly.
of the
Yep.
European space agencies do.
Yeah. ESA,
Yeah,
yeah, European Space Agency only opens doors to, I think, European cooperating states, and UK is also one of the European cooperating
exactly.
state. But
Yeah, yeah,
but even to work for ESA, you should have a UK citizenship. I mean, India is nowhere on the map.
yeah,
So I mean,
yeah,
unfortunately, yep.
yeah. That's a
Yeah.
bit unfortunate. Okay,
So
thank you
you
so
are
much,
studying
Leila.
in TU Delft?
Yeah, I am.
Oh, so you're doing
Yeah.
masters in aerospace there?
I'm doing masters in electronics actually, but I'm
Okay.
working on a project
I
for
have
space.
heard a lot. Yeah, I've heard a lot of good things about TU Delft. I mean, I have seen it because when I was applying for my masters, I also applied to TU Delft.
Yeah,
But yeah, I got into it, but I chose to come to UK because I mean, I was
yeah.
looking out that what are the biggest producers, aerospace
Engineers.
manufacturers and
Yeah, makes
producers
sense.
of the.
Makes
Yeah,
sense.
exactly. US and UK are the
Yeah,
top players. I mean, obviously, US and Europe in general. But
yeah.
yeah,
True.
the astrodynamics research in TU Delft is extremely amazing. I must say that. Yeah.
It is. It is. Yeah.
Yeah. All right. Yeah.
Yeah.
Lovely
Thank you
meeting
so
you.
much,
And
Rama.
you can
Yeah.
get in touch with me on LinkedIn. You can just search me up and
Yeah. Yeah.
yeah,
Yeah.
yeah,
Yeah.
yeah.
I
Let's connect
already
and
did. Yeah.
discuss.
Yeah.
All
Yeah.
right.
For sure. Thank you
Yeah.
so much, Brahma.
Thank you. All right.
Yeah.
Welcome. Welcome. All right. Any more doubts? Does anyone have any more doubts, questions they want to ask me? Okay. So if no one has any doubts, I'll just terminate the meeting. Okay, Pratik. Pratik,
Uh, Very good. Good evening, sir.
good evening.
Sir, I'm from mechanical engineering background, sir, and right now I'm
Mm-hmm.
working in National Aerospace Laboratories as a
Oh
project.
wow, CSIRNL. Yeah, I've
Yes,
heard of it.
yes, sir.
Yep.
As a
I have
design
some. Yeah,
design
I have
engineer
some
working.
connections. Yeah, yeah, I have some of my seniors working there. Yeah, please go ahead, please.
Sir, I wanted to ask you about role of space robotics in this missions of Titans and future missions. What will it play the robotics role? Space robotics, sir. Because
Definitely, yeah. See, space robotics is very instrumental, but I would say space robotics will play a big role in situ planetary exploration vehicles, in my opinion. More specifically, in sample return missions. Like you have like many missions, sample return missions from Moon and Mars, right? Wherein the rover collects the samples, Martian sample or Moon sample, and then it analyzes and determines its composition. I definitely believe that, and NASA also has a challenge every year to develop a robotic arm, right? So I think, yeah, space robotics is gonna play a big role. And
because
yeah,
I've seen a lot of rovers are only going for missions. I have not seen any more drones, aerial or You can say
Exactly. In my presentation, yeah, this was exactly my point during the presentation. So aerial vehicles, the concept of aerial vehicles specifically for planetary exploration is a little bit booming right now, because as I said, till date, the only aerial vehicle which has flown in a planetary atmosphere is NASA's Ingenuity helicopter. That's it. No other aerial vehicle, right? But slowly, people in space agencies, scientists in space agencies have come to realize that drones can actually be a very good tool for planetary exploration. And obviously, if NASA's Dragonfly mission to Titan becomes successful, that will be the first drone to fly on Titan, right? So obviously, there is a technology demonstration aspect here. So the feasibility of using drones for planetary exploration has to be fully established. In space agencies, we call it TRL, technology readiness level, right? So drones don't have that high TRL. So once they have a good TRL and once they are tested and proven in a lab simulated environment here on Earth, then definitely we can have confidence to launch drones into space and for planetary exploration.
yes, sir. Thank you, sir.
Yep. All right. Thank you. Any more questions? I think we can end the meeting here. All right. Thank you so much, everyone, for joining. And if you guys have any question, you can come in touch with me via my email ID. All right. Thank you.